Hi there, my name is Luke Cole, and I'm going to be going over the key points of software delivery and operations for monolithic and microservice architectures. On the agenda today, we'll be going over a monolithic e-commerce platform, a microservice sales as a service, SLAs and SLOs, deployment strategies, and summaries and key takeaways. So, firstly, this slide outlines the monolithic architecture designed to meet core stakeholder needs. We needed zero downtime, high availability, simplified recovery, automated CI/CD, scalability, and cost efficiency. First, we implemented a robust VM-based deployment strategy using the N+1 redundancy model to ensure no single point of failures, and our capacity planning allows for 40% headroom. The platform can tolerate faults and scale predictively to meet 100 transactions per second using only 4 virtual machines based on this planning. If, for example, we had to increase TPS, we'd have to review this and scale accordingly. Secondly, we introduced a secure and auditable CI/CD pipeline aligned with ITIL 4 change control. We have manual gates that are used for sensitive phases, supported by RFC and CAB process to manage risk and ensure stable deployments for any changes raised, especially crucial for stateful applications like this. Thirdly, to support the SLA-driven observability and recovery, we ensure 99.999% availability. Recovery time objectives is set to 1 hour, and the recovery point objective is set to just 15 minutes. This is achieved using full stack monitoring via Prometheus, Grafana, and Elk Stack, along with database backup and rollback automation. Overall, the design ensures a stable, observable, and cost-effective deployment suited for stateful transaction-heavy monolith platforms. And as you can see in Figure 1, we've explored a singular monolith and a modularized monolith based off cohesive and highly coupled functionalities within the domain. This slide presents the microservice-based sales as a service architecture designed to meet stakeholders' needs around, again, zero downtime, again, high availability, but now with cloud architecture in place, we can look to explore regional failovers and multi-tenant scalability. Firstly, we implemented a scalable and secure cloud-native architecture using the AWS EKS clusters and Istio service mesh. Data is encrypted at rest and in transit, while multi-region clusters ensure fault tolerance and resiliency. This foundation allows for secure horizontal scaling and regional high availability. Secondly, we apply a progressive delivery model. Canary deployments are used to verify small batches of traffic before full rollout, while blue-green deployments handle critical components like the authentication and user management aspects of the domain, ensuring zero downtime rollbacks. Quite crucial for sensitive apps like that, which can have mass disruption if things go wrong. These approaches balance risk, speed, and availability. Finally, the architecture aligns with 12-factor app and zero trust principles. Services are decoupled, stateless, and independently deployable for the most part. Security is enforced through RBAC, MFA, Vault for secret management, and OWASP compliance across APIs, ensuring strong governance and protection of PII across tenants, as obviously this is going to have some PII integrations at some point based off the nature of the application. And this architecture ensures high scalability, resiliency, and secure CI/CD automation, making it ideal for complex distributed sales as a service applications. Now, just to expand on the microservice domain and look at failovers and the infrastructure of scale, this slide illustrates our global microservice deployment strategy for high availability and resiliency at scale. We've deployed services across 3 major AWS regions: US West, US East, and the EU. Each region hosts independent Kubernetes clusters with identical node groups and services, ensuring workload consistency and fault tolerance. A GTM, otherwise known as a global traffic manager, such as Akamai, sits above all regions and intelligently routes user traffic to the nearest healthy region based on latency and availability. With Akamai as well, it helps us to mitigate DDoS attempts if there was something that anomaly happening from that front, so it never actually hits our service. Each region is capable of running the full workload independently, and if one region suffers an outage, whether it's US West, East, or the EU, the system fails over automatically to another active region. This prevents customer downtime and ensures continuity within whatever their user journeys are. Replication mechanisms keep data synchronized across regional data stores, and Kubernetes autoscalers ensure that resource adapt to demand within each region. So if traffic starts to spike and we need more pods, or because the service is not doing too great, we can scale accordingly. And also on the cost effective side, if for example we reduce TPS across some applications, we can scale back and meet accordingly. So it might cost more, it might cost less, but it'll balance out. But the main point is being highly available and having that strategy in place. This architecture underpins our SLA target of 99.999% availability. And ultimately, this setup allows us to serve multi-tenant clients globally with minimal latency, resilient failovers, and rapid recovery from outages. Now, moving on to SLA and SLOs. These are crucial for managing service expectations and ensuring reliability whilst having a clear outcome for any breaches. SLAs are essentially formal agreements between service provider and customer, or maybe even between internal services themselves. SLOs are internal targets to ensure teams achieve the service levels we've promised in our SLAs. So this slide presents the key SLA and SLO targets, just a few out of the many that I've listed in my appendix for the monolithic application, focusing on availability, performance, and operational resiliency. The primary metric is a 99.999% uptime, achieved through high availability VM clusters, intelligent load balancing, and roll deployments with integrated monitoring. Supporting this are three critical secondary objectives, if you like. First, an infrastructure RTO of approximately 1 hour, made possible with automated backups via VM snapshots and fast redeployments using Ansible playbooks. Secondly, we target a mean time to detect of around 3 minutes, leveraging Prometheus and Grafana to detect and raise alerts as soon as failure conditions are met in real time, and notify teams in external communication tools like Slack, Microsoft Teams, etc., as integrations to post exist. And thirdly, we aim for API latency below 1 second at the 99th percentile, using circuit breakers and load balancing to keep user experiences fast, even under load and error scenarios, if you like, from the circuit breaker front. And also to cut calls if traffic was unnecessarily calling us and we can't serve traffic back because the state of the circuit breaker is now open. So we can relieve needing to make unnecessary resource commitments to calls that aren't giving us any benefit, so we can save that resource. And when the circuit breaker recovers, we can then get back to BAU returning traffic. These SLOs support a resilient and responsive platform that meets both technical and business demands for uptime, speed, and incident response. Now for the microservice SLAs and SLOs. So this slide details the SLA and SLO targets for the SaaS platform. Our primary objective, again, is 99.99% uptime, which we deliver through a multi-cluster Amazon EKS setup. This architecture spans multiple AWS regions, as previously mentioned, and availability zones. This allows us to isolate faults and maintain service continuity during outages, as mentioned previously. We use network load balancers that play a critical role by distributing traffic efficiently across healthy pods and clusters, with health checks and failover logic built in. These NLBs are reached by GTMs, as you've seen previously. This ensures requests are always routed to available services even during infrastructure disruptions. Additionally, we use Istio as a service mesh, which introduces intelligent traffic routing, circuit breaking, retries, and mutual TLS for service-to-service communications. For secure service-to-service communication, It enables granular control and observability over internal traffic too, reducing the risk of cascading failures. Combined, this setup supports full isolation, seamless recovery, and secure zero trust traffic management, essential to sustaining our uptime commitments. The rest of our SLA metrics, such as rollback within 5 minutes, under 1% change failure rates, and RTO, RPO targets, are enforced through GitHub, through Argo CD, progressive delivery strategies, and automated data backup and failover systems. Now moving to deployment strategies, which are a big part of becoming successful, involving changing our organization, processes, tools and techniques, and reshaping our entire approach to testing, security, and measuring quality. And our KPIs were met by introducing the following setups. So before I say what setup we decided. We explored a few. So we explored blue, green, rolling deployments, immutable, and canary. This slide is obviously talking about blue, green, and rolling deployments, and comparing the two deployment strategies evaluated in the project. On the left, blue green creates two identical environments, one live and one non live, otherwise known as idle. Deployments go to an idle environment and traffic is switched when validated. The approach provides zero downtime releases and simple rollbacks, making it suitable for critical service like authentication. However, the drawback here, which doesn't meet our stakeholders' requirements for cost efficiency, is that it doubles infrastructure cost and expands the attack surface as both environments are exposed temporarily. So, not ideal for the VM based infrastructure. On the right, rolling deployments replace application nodes incrementally, maintaining service availability during updates. It's highly cost effective and offers naturally high availability, ideal for stateful monoliths where gradual rollout and safe rollbacks are important. However, rolling back in the event of a failure is more complex than blue-green, as it may require redeploying the entire previous version by node. After the comparative analysis in Appendix D, rolling deployments was selected for the monolith architecture due to the balance of resiliency, cost, operational autonomy within CI/CD pipelines, and meeting stakeholder requirements. Now, moving on to the other two, we explored two additional deployment strategies: immutable deployments and canary deployments. Starting with immutable deployments on the left, this approach replaces the entire infrastructure with a new version. No updates are applied to existing instances, instead, new ones are provisioned. While this ensures consistency and reduces the risk of configuration drift, it's often too resource intensive and slow for dynamic sales as a service environments where speed and partial rollouts are preferred. On the right, Canary deployments offer a progressive delivery model where a small portion of traffic is routed to the new version before rollout. This allows real-world validation with minimal blast radius. If an issue arises, rollbacks affect only a minor segment of users, so it's not totally, mass blackout, shall I say, and it probably will be unnoticeable in a good happy case scenario. In our microservice architecture, Canary was selected due to its fine-grained control, real-time risk mitigation, and synergy with service mesh routing and automated rollout tools. It also enables high availability, fast feedback, regional isolation, aligning closely with modern DevOps goals. Not to mention as well, blue-green was also decided to be used for authentication apps, as I mentioned previously. Now CI/CD. Automated a basis for regression, enabling teams to fail fast and gatekeep production changes. It's very important for us to get right, and all layers of the testing pyramid is covered across pipelines. So this diagram represents the monolithic CI pipeline, continuous integration from code commit to production. The reason why it's continuous integration is at some point there is a manual intervention deployed to production to obviously gatekeep any changes, as it is safer that way and is done by a DevOps. This is ideal for monoliths, as obviously it can incorporate big bang changes, and having someone there to roll out and be in control if something goes wrong is critical, to not have disruption, regardless of the deployment strategy being used. So we begin at the local stage where developers build, test, and push code. This triggers the CI, which compiles code, runs unit tests on the image build, and builds a Docker image and performs security scans. From there, the pipeline moves into dev, where the image is deployed and automated. Functional tests are then used to validate black box behaviors, and to confirm the app is working functionally as expected. And once successful, the image is promoted forward. Next is user acceptance testing, which consists of both stubbed and unstubbed environments. Stub testing mocks downstream service for isolated validation, whereas unstubbed in UAT integrates with real services that are also in UAT environments to simulate real world conditions. Stage mirrors the production environment with a split like stubs and integrated tests. Extended non-functional testing also occurs, and runs resiliency, soak, and load testing to verify production readiness under high TPS. And once validated, the release enters production via a canary deployment approach. A subset of users is routed to a new version, and if no issues arise, full rollout proceeds. This progressive approach ensures high confidence and minimizes production risk, crucial for a monolith where rollback and issues can impact the entire platform. Now, this slide shows CD, continuous deployment pipeline for a microservice-based SaaS platform implementing a progressive strategy. The reason why it's CD is because the moment you press builds from local, you are automatically waiting on crons to roll out your changes to the next environment and then progressively to production at some point within a few days. Though, yeah, with that said, they can be manually overwritten. So if you wanted to quickly build out your app and release, you can manually invoke those promotions. They're not suggested. So it starts at the local environment where developers push code, trigger the pipeline. The CD build phase compiles, tests, and versions and packages the service as a Docker image. In the dev phase, we enter stubbed and functional test stages, and we also run NFT tests as well. Each stage increases test complexity and realism with the integrated test verifying interactions across microservices. And as you can see, under stubbed NFT in the dev layout, there's org1, org-n. We deploy to different, regions. We like to call them like org or regions just for simplicity. But yeah, the idea is to be able to roll out to an isolated environment where we run closer to that localized area. So deploy to US West, US East, and then EU. We can run NFTs in separation to those data centers. Once the test passed, the pipeline promotes the image to extended testing, where extended NFT runs extensively overnight. So again, no different to the other NFT testing. Soak, resilience, and performance under peak load is now run and is successful. Promoting to Canary prepares the release candidate. In production, we begin with Canary deployments to a limited region and run smoke tests. The next morning, the CD check before promote release verifies system health. If clear and all is working fine, the promote release publishes the image to all regions, followed by a CD deploy prod, which rolls out sequentially to each production region, minimizing risk. This strategy balances safety, speed, though a bit slow in getting out to prod in later environments for good reason because of the prolonged NFT testing. But as mentioned, this can manually be triggered. And we have observability and monitoring to ensure that all the apps that we do release are healthy and the data is being viewed in real time. The summary and key takeaways. So to conclude, there are 3 core takeaways from this project. There are many more, but this is only one slide and I've only got 20 minutes. First, the SLA and SLO targets aren't just performance indicators. Also, not to mention service level indicators as well, but they are embedded into how we design for reliability. By aligning around RTO, RPO, latency, and uptime, we ensure services are not only performant but meet clear, measurable expectations, as we saw with stakeholder expectations in Appendix A. Secondly, CI/CD plays a crucial role in delivering safe, frequent changes, and through automated testing, looking at a test pyramid with all the layers there to help serve as a basis for regression and to also ensure high test coverage before making any releases to each independent service. We can then do deployments and rollbacks in the event that obviously things go wrong, and we minimize risk and ensure that delivery aligns tightly with both stakeholder expectations and business operations. And finally, architecture must evolve with scale and complexity, starting from monoliths deployed on resilient VMs to cloud-native microservices spread across different AZs. Each decision has to reflect operational risk, agility, and the growing demands of the business and its users. Together, these pillars shape the foundations for a secure, reliable, scalable software delivery, as I discovered through my analysis, investigations, and then obviously the implementation of this deployment plan and strategy. Right, thanks a lot for watching. That concludes the presentation. Have a lovely day. Thank you.